Tim Holtkamp from Buss-SMS-Canzler and his talk about efficient drying solutions, saving energy with contact dryers. I'm very excited. So, Tim, the stage is yours.
Yes, I've been working in my company, Buss-SMS-Canzler, for 6.5 years now, and we are a supplier that is already over 100 years old, and we supply tailor-made process equipment, and we provide, in my eyes, very interesting drying solutions by the use of so-called contact dryers. Our head office is located in the center of Germany, close to Frankfurt. There we also have our fabrications. We have a small branch office close to Cologne in Düren. There we have some engineering activities. One small office in Erlangen in Bavaria, where we perform CFD and DEM simulations, as well a place in Switzerland close to Basel and Pratteln. That's where I'm located, where we have our process development. And there we have our own laboratories where we can perform laboratory trials with our customers. We have even bigger metal pilot plants where we perform pilot trials for scale up and further feasibility. And also, in addition to that, a partner lab where we can make analysis. And as I said, CFD and DM simulation for accompanying analysis. We are also active in the process equipment for evaporation technology with our thin film evaporators and with equipment for the treatment or processing of polymers. But today we look at this drying technology, which is called contact dryer. So because I think that just a few people will know this technology, we will first of all have a look on the physics of this technology. Most of you probably know the kind of dryers that you see here on the right side, and also this kind that just Markel Alberdi from Econec has just presented to us, which is the so-called convection dryer. So a dryer that you all know also from everyday's life when you come out of the shower with your wet hair, and then you take your hair dryer and blow hot air over your hair, and then the hot air will saturate with water and the hair becomes drier, and then the wet hot air leaves this system. Yeah. So this is a classical convection or convective dryer. On the other side here, on the left side, you see our drying systems. We call them contact or conductive dryers. They do not use air at all. So we don't have an inert gas here. What we have is the product, the wet product that is brought in contact, in very close contact to a heated wall, for example, a double-jacketed machine with a thermal oil in it or steam in it. And the heat will be transferred through the wall by conduction into the product. The product heats up, and then the water, for example, starts to evaporate. And inside the dryer, we just have pure vapors and nothing else. So, but this, supposedly small difference has really far-reaching consequences. Yeah, and I will explain to you these consequences later. Just to give you an impression how a setup can look like. With a contact dryer, we have here, for example, a thin film dryer, which is a cylindrical machine with a double jacket where the thermal oil, for example, is circulating. We have a feed nozzle where the wet product is pumped in. We have an agitator that presses the wet material against the heated wall and then pushes it down slowly where it's being dried, and then it leaves in the bottom, and the vapors go counter currently in the other directions, and they can be externally condensed. One, let's say, level of abstraction higher, we can summarize this picture here as a general, very easy setup for contact drying. So the contact dryer in the center, a heating unit besides, a feed system, an outlet system, and an exhaust nozzle. On the right side, you see a comparative system with a convection dryer. There you see this green flow, which is one more and very big flow. This is the flow of air, yeah, that in the previous presentation was talked about a lot. Yeah, this could be reduced a lot in this pulse spray dryer. But here, so in our drying systems, we don't have this, yeah, which make the systems much more easy, simpler, less complex. In both cases, you can try to recover energy. In our case, we can recover the latent heat completely, nearly completely, and also we have the full recycle of the solvent that we have just evaporated. This is only partially possible with convective dryers. So, and then I've looked into literature and I found the Bible of drying technology. Here you can see it from K. Gröll, Trocknungstechnik, second edition, page 536. I found the complete energy balance. You can see here the streams for a convective drying system. And then I took these values and I simulated the same for a contact dryer to have a comparison between these two worlds. And what I figured out is that the energy consumption in the convective dryer is approximately 14% higher, which is actually not so much than I expected, but it's still there, this difference. Actually, the thermodynamic limit would be 0.64 kilowatt hours per kilogram of evaporated water, which is corresponding to the pure evaporation enthalpy. So the net energy consumption, including the very good energy recovery we can achieve in our dryers, is 475% more in convective dryers. That's because we can only recover approximately 60% less in the convective dryers than in our drying systems. And also very interesting, what is the temperature of recovery? We can recover the energy in a condenser that you can see here, yeah, at nearly the boiling point if we use, for example, a mixing condenser, whereas to condense the water from the airstream that leaves the machine or the dryer, the convective dryer, can only be recovered at very low temperatures, which makes this energy pretty useless in my eyes, but this can be discussed. In addition, we have this big stream of 1,700 cubic meters per hour of air, which is not present with our dryers. So how can we recover this energy? The big question of energy recovery. We can implement our dryers in many ways. First of all, the vapors can be directly used. Yeah, they have 100 degrees boiling point of water at atmospheric pressure, for example. So you can condense them anywhere, or you can condense them in a mixing condenser and then use, for example, 95 degrees Celsius hot water to preheat something somewhere else in your plant. But what I also wanted to tell you, which I think is very interesting, what is future, because it can help you to electrify your process, is that you use a heat pump. For example, here on the left side, you can see an open loop heat pump, or we call it mechanical vapor recompression. So you use the steam that comes out of the machine, maybe just part of it, and then you compress it with a fan or blower to a higher pressure level, for example, to 160 degrees. And then you can use it self-sufficiently to heat your own dryer. We have not yet done that actually, but I'm very open to talk with you about that. Yeah, if you have possibilities or if you want to go this way, we are very open to go one step further into this future. But you can also use, if you want, a closed cycle heat pump, the classical heat pumps that you know from your homes, where your vapors are condensed inside the heat pump, and then in a secondary circuit you can use the pumped up heat for your own dryer or for somewhere else. So I've found out or figured out two rules of thumb that can be applied when you want to validate the use of self-sufficient heat pump system. I would say they pay off faster the smaller the dry matter amount is in your mixture that you feed into the dryer, and the further below 1 the ratio of price per kilowatt hour of electric to fossil energy is, including CO2 taxes divided by the COP of the heat pump. That's so complicated. That's why I fear the formula. Just divide the price for electric energy by the price of fossil energy. For example, this can be 2. And then you divide by the COP, this is the coefficient of performance of the heat pump, which, for example, in case of this value to be 2, this whole ratio gives 1, this would be the critical point where you say, okay, this doesn't make sense. But if the COP is bigger, and that's very probable, then we are below 1, and then you can really look deeper into this topic. To summarize, our machines or our dryers are a little bit like a distillation plant, like an evaporation. So for us, it's very easy to have a vacuum process to lower the boiling point, to lower or to make the process more gentle. We don't have oxidative stress because we don't have air inside our system. So this makes the system pretty simple, pretty compact. The energy consumption is very good. Energy recovery is high at a high level of temperature. Material recovery, so closed solvent circuit is nearly 100%, so that we can meet ATEX requirements or really toxic solvents or whatever is inside your product. Yeah. Some neutral points, I would say, sometimes we have problems with crust forming products. Yeah, here I think convective dryers are much better. Yeah, but we have also invented a very, very good solution to to meet this problem, which I will show to you later. And in its very basic configuration, I think a convection dryer is a little bit more gentle with regard to the product temperature. So let's come to our dryers and the application of our dryers. We can feed into our dryers actually anything, everything you can imagine. So we can feed solutions, light solutions or dispersions that are completely liquid. We can feed liquid but pumpable slurries, no problem. Yeah. But the critical things are then the pasty sludges. We can also, without any problem, feed them into our dryers, and they are then further dried, but also wet powders. And then what you get out from our dryers are in the end powders or granules. But unfortunately, we don't have really the control over the size and distribution of the particle size. That we always say it happens as it comes in the end. So let's now see how our dryers look like. Have a look in our SMS dryer family. We can distinguish two kinds of dryers. On the left-hand side here, our low hold-up thin film dryers. Yeah, we have a vertical one, the CP dryer, and the horizontal one, the D dryer. Please, for questions and answers, I don't know why they are called CP or D dryers. I have no idea. And on the other hand, we have the large volume dryers. And here I will just show to you our CFT dryer. The vertical and the horizontal thin film dryers, they have very short residence time and the plug flow-like behavior. So residence time inside the dryers is really either a couple of seconds or just a few minutes really. And on the other hand, the CFT dryer is a backmixed dryer, so no plug flow-like behavior. Here we have residence times that exceed some hours. Let's have a look at the low hold-up dryers, the thin film dryers. You can see here in the background a picture of the rotor of our vertical CP dryer. It's characterized by a flap rotor or pendulum rotor, as we call it. This CP dryer is very good for crystallization, for salt solution evaporation with sudden phase transitions. And we can feed into this machine liquid to light slurries. On the other hand, we have our general universal weapon, our horizontal D-dryer. This can be fed with everything that is also liquid, but mainly pasty and dry powder, wet powder. The setup of here, in this case, a horizontal D-dryer is a classical distillation setup. You have the horizontal dryer with a double jacket, heating medium inlet and outlet. We have the feed, can be realized with an eccentrical screw pump or a twin screw or a single screw. And the product will be fed into the dryer. The rotor takes it up and then pushes it to the right, and then it will be dried and falls out of the dryer with a rotary valve or a gate valve. Counter currently, the vapors will leave the machine, for example, through a dust filter, and then the vapors can be 100% condensed in a condenser. The same is true for the vertical machine, but just that the machine is vertical, so feed goes in the top and leaves dry in the bottom. The working principle of a thin film dryer is actually pretty simple because the name already says you that the rotor inside the dryer will form a thin film on the double jacketed internal of the shell, and then the heat will penetrate the metal, penetrate the product. We have here a remixing situation in front of the rotor blades, and then the product will heat up and start to evaporate. The horizontal dryer has rigid elements or rigid rotor blades, whereas the vertical machine has pendulum rotor blades, which are very good for hitting crusts away. The temperature profile of your product inside the dryers, the thin film dryers, is very similar. So here we have the dryer axis in black, feed inlet, dry product outlet, and here the temperature axis. Here on the right side in red, we have the temperature of the thermal oil or of the steam on the heating side. And then in blue, the product that comes in maybe at room temperature, then it heats up, heats up, heats up until we reach the boiling point, in this case, maybe of water, of any solvent. And then we enter into the first drying section, which is the superficial drying of your solvent. So in the drying section, we evaporate relatively temperature neutral, and then we reach a critical point. This is the phase transition, where we have the transition from liquid to solid. There we go through a very viscous, sticky phase, and then the horizontal dryer and the vertical dryer take different ways. It's clear that when we are solid, that the product in the vertical machine will not stick to the wall anymore. It will just fall down and leave the process. So then the drying is over. But in the horizontal machine, we still remain in the dryer and feed further up and enter into the second drying section, where we try to evaporate the capillary bound moisture or solvent. So this region here is mainly dominated by diffusion. Let's now go to the other class of large volume of contact dryers, which is the large volume dryer. We call it CFT dryer. That's very good for crust forming products, liquid or slurry feeds. We have a direct phase transition inside the dryer. Granulation is possible here, and it's also ideal for poisonous waste streams. Here you can see a picture of the internals of the pedals of this dryer. It's actually not so easy to understand how this dryer works, but I always say that it is a mixture between a fluidized bed dryer and a contact dryer. Contact dryer because there is no air inside, and fluidized bed dryer is because you can see here a DEM simulation. The puddles create a fluidized bed in the bottom of this partially filled machine. So, but how does this work? So we have exactly like with the other dryers, a double jacketed cylindrical machine. We have a rotor inside that moves, in this case, the pre-fill, so the bed that is already inside the machine. And then we have inlet nozzles that feed directly in this hot bed. And in the moment that the wet product reaches this bed, it will directly evaporate in situ in this hot, very hot bed. The bed locally will cool down a little bit to provide the evaporation enthalpy, and then everything around is dry. So this means before the sticky phase transition area touches or can touch the wall, it is already dried. This is why this kind of dryer is used for really crust forming products. The temperature profile in this backmix dryer is, as you can see here, so we have the dryer axis here in black again, and we have the temperature axis here in blue. The heating temperature is uniformly over the whole length of the dryer, approximately 18 to 100 Kelvin above the boiling point of the product that you want to evaporate. and the bed temperature is somewhere in between. Yeah, and there where you can see the nozzle, these little slopes here, there is the inlet nozzle of the wet material. So there we have a little temperature sink, and the lower the feed rate is into your dryer, the higher the bed temperature with its maximum, that the bed temperature is the same as the heating temperature, and the higher the feed rate, the colder the bed will become up to a critical point. This is what I call the bed collapsing point. That's when the bed is getting too cold and it will collapse, so there is no fluidized bed anymore. The setup of the setup of this dryer is also a classical distillation setup, with the difference that the feed nozzles are here evenly distributed on the top and over the whole length of the dryer. And since it's a back mixed dryer, we have on the right side here a calming zone where this fluidized bed starts to calm down a little bit, and a wear over which the solid particles that are really already bone dry will then exit the machine, and they are discharged via a rotary valve or a gate valve. So that is our sales team and some of our representatives. And I thank you very much for now for listening to me and for your interest. I hope you have some questions.
Yes, right. Thank you very much, Tim, for the interesting presentation. As you said, you can now ask your questions over the F&A button at the bottom of your screen. So please feel free to ask your questions. And also everyone who is now joining on LinkedIn, please feel free to ask your questions in the commenter section, so then I can also forward it to our speaker, Tim. So I will wait a few moments that you have time to type in your question. And maybe for now, one general questions from you, from me. Into what countries do you export your machines?
Actually, over the years that our company has been existing, we have developed a really broad network, so we deliver everywhere except for the sanctioned countries. So right now, I think not Russia and not I don't know, Venezuela or something like that, but normally all over the world.
Okay, perfect. Thank you.
And we also have our service, everywhere in the world, so this is not a problem.
Okay. And one question is coming in over the F&A button. What about the saving energy by vacuum operation?
Yeah, vacuum operation is an interesting topic here because our dryers work with the principle of evaporation, like a distillation, which means we have to always preheat our material to its boiling point. So if we suck vacuum, then this boiling point is lower. So for example, I don't know, 100 degrees water boiling point at atmospheric pressure. Under vacuum, we can have a lower boiling point, which means that the preheating energy input is not needed anymore. Yeah, for example, because we evaporate at 40 degrees.
Okay, thank you. Hope this question is answered. And one another question: if you have excluded or you have excluded the reactor term from your presentation, is there a reason for this?
There's not, it's actually a little bit too long for the presentation, and we don't use this too much as a drying device. It can be used for this, but it is also used for like a simultaneous drying and reaction. That's because it's named reactor term. So in the end, it's a kneader. We can imagine to perform chemical reactions in there where dry material can go out in the end. Also, the treatment of pyrolysis residues and so on are possible, but that's an own chapter. That's why I've not included this into the presentation.
Okay, thank you. So we have another questions over the F&A button. Have you looked into steam recompression coming out of a dryer operated at vacuum pressure?
I don't know if I understand this question. So I think I try to understand it. So vapor recompression in combination with vacuum inside the dryer means, how about we use our dryer under vacuum, we operate it under vacuum, and instead of condensing the upcoming streams in a condenser, we directly let the steam go through the vacuum pump and compress it then. So, and what is the question now?
So the question was if you have looked into steam recompression coming out of a dryer operated at vacuum pressure. But if the question is not answered now, it's also okay that the asking person can also maybe find out what's the actual question is.
So
And
the thing is, in the end, steam recompression, if you are under vacuum, the density is pretty low of this steam. Yeah, so this can be maybe a little bit difficult, but it's possible. Yeah, the blower
okay.
needs to be very big due to the low density of the steam in the
Okay.
vacuum.
Perfect. So thank you for for answering this question. And the last question, I think, is it possible to selectively condensate the solvent when it is a mixture solvent?
Yes, absolutely. You can treat our systems as any kind of abnormal standard evaporation. So you evaporate in our dryer a solvent mixture. We often have this case actually. And then you can recondense this in a column directly on top of our dryer, yeah, with a partial condensation, for example, in the top. And then you have a washing column and you can directly separate or split this mixture in this column. This is possible, yeah.
Okay, perfect. So I think when no questions are left, thank you very much for your presentation. If some questions are not answered now, please feel free to ask the questions to powertech-technofarm at nürnbergmesse.de. We will forward it, or ask Tim Holtkamp directly the question. So thank you very much, Tim, for your interesting presentation.
You're welcome. Thank you.
Thank you.